how's it going, everybody? I am here on Tuesday, May 4th, and we are looking at our last video of the semester here. We're going to talk about transformation matrices today. In our last video, we looked at, introduced the idea of matrices. We looked at addition, subtraction, scalar multiplication, and matrix multiplication in the last video, as well as the determinant of a matrix. And today we're going to apply some of those operations to a concept associated with shifting some points around in the plane. Recall the problem that we had set up in the last video. That was sort of like our goal for this week to be able to answer. In the previous video, we were looking at this problem here. A triangle is formed by these 3 points in space. What we would like to do is determine how can we go about rotating those 3 points in space by a certain number of degrees. And what we're going to do along the way today is we're also going to look at several other matrix transformations. So this is our one that's most directly tied to our concept of angle manipulation that's associated with trigonometry here. But there's lots of transformation matrices out there as well. So we're going to look at several of them. One of them will end up being a rotation matrix, and it's going to help us perform this task much, much easier than what we did in the previous video, right? In the previous video, it turns out we learned that we can actually already do this problem, but it takes a whole lot of work. And what we know is that there's a ton, absolute ton of applications associated with these transformation matrices. And what we want to do is to be able to do this computation incredibly efficiently, or rather than having to do a whole page of math every time we move a single pixel on a screen, right? So again, our goal today isn't just to do this, but to do this efficiently. And the most efficient way that we can do this is with some matrix transformations. So in this video, we're going to look at several ways to manipulate the locations of a point in the plane using a matrix operation. So let's go ahead and do that here. What we'd like to do is explore how matrix multiplication can alter the location of a point in two-dimensional space. We're going to see if we can form some generalizations about how and why those matrix operations do what they do. And so to get started, what we want to ask is what matrix multiplication should we even be doing here, right? So what we're going to want to do is we're going to want to represent an xy point in space by some sort of matrix or vector. And then we want to multiply it by some other matrix or vector to alter the location of that point in space. So our first question should be, if we consider the point xy in the form or an xy point to be in the form of a vector, a column vector xy, then my question to you is, what dimension should our transformation matrix be so that when we multiply by this transformation matrix, we'll get back another point in space that will also be a column vector xy. So here's the thing that I'm thinking here. It seems to me like xy, I know, is going to be, this has 2 rows and it has 1 column, right? This is a 2 by 1. What we want to do is we want to multiply this by something so that on the other end, we're going to get out something that looks like, oh, excuse me, sorry, I'm setting this up backwards to the way that I want to do this here. Yeah. Sorry, I'm gonna shift these around a little bit. What I'm going to do is I'm going to put my transformation matrix first right here. So I'm going to get a transformation matrix here, which we're unsure of what this dimensionality is going to look like. What I'd like to do is multiply this by a point vector right here. This is our xy. Right, this is our unknown multiplication sitting right here. And what I know is that this xy is a 2 by 1. And what I am wondering is, if my interest is to get back a x prime, y prime, my new location in space, I'll call this p prime, and this is also 2 by 1, then the question is, what dimensions do I need for the object that is sitting here as my transformation matrix? Well, what we learned in the last class is that we need our inner dimensions to match if we're going to be able to do the multiplication at all. So based on that, what I know is this dimension has to be a 2 so that it matches this 2 so that the multiplication is legal at all. The other thing that we learned is that the resulting dimensionality that we're going to get after doing the product is going to be based on the outer 2 dimensions. So the missing one that's sitting right here and the one that's right here. What we'd like to get back is a 2 by 1, so it seems like this needs to be a 2 by 2 here so that the inners match so that it's legal, 2 and 2. The outers, 2 and 1, determine the final dimensionality of the resulting product on the other end out there. So it seems to me like we're going to be wanting to multiply by a 2 by 2 transformation matrix. So I'll be calling that ABCD right there. It seems like it needs to be 2 by 2 for our transformation process to work out dimension-wise, right? So the first question we're even asking here is like, how do we even know what size matrix to multiply some point by to transform it? And what I can now see is the only way you are going to multiply some matrix by a 2 by 1 to get back another 2 by 1 is if that something was a 2 by 2. We can kind of do the dimension math right there to determine what must be the dimensionality of this unknown transformation matrix that we're going to want to look at today. So it seems like we want to multiply our 2 by 1 point vector by a 2 by 2 transformation matrix if we want to get out another 2.1 point vector right there. So all the operations that we'll do today will always look like a 2 by 2 transformation matrix multiplying by either 1 point or many points. And we're going to start with just 1 point here, and then we'll upgrade it, right? So let's go ahead and look at a couple examples. And very importantly, remember, today's goal is intensely graphical. This is very much a graphical concept that we're looking at here. This wouldn't be anything that's very interesting to us if we weren't drawing a picture for every single example that we did. Right? We want to know how these transformation matrices affect points in the plane. So we're going to draw a quick graph for every single one of the results that we get here today. So as our first examples, let's go ahead and perform the matrix operation, then graph the before and after points and interpret the impact that the transformation matrix had on that point. So you should see that in all the examples here, we have a 2 by 2 matrix multiplying a 2 by 1 matrix. We know that that's going to result in another 2 by 1 matrix on the other end. Right? So in our first example here, our transformation matrix is 3, 0, 0, 1. We are multiplying by the point matrix 2, 2. So that says to me my point 2, 2, I can graph that right there. There's 2, 2. There's my P point right there. What I would like to do is do this multiplication, find the 2 by 1 that we get out on the other end, and then graph that guy as well. And I'll go ahead and call that guy P prime. So remember how our matrix multiplication worked from the last video. We're always taking the dot product of rows of the first object and the columns of the second object here, right? Our first object is a matrix, our second object is a column vector. So in our first one, the dot product of 3, 0 with 2, 2, I'm going to do 3 times 2 to get 6, plus 0 times 2, which is 0, and 6 plus 0 is just going to give me 6. Since that was the first row times the first column, I put my result in the first row, first column of the resulting vector. I also want to get the second row first column of my resulting vector, so I'm going to do the second row dotted with the first column of my product over here. So the dot product of 0, 1 with 2, 2, we're going to get 0 dotted with, 0 times 2 is 0, plus 1 times 2 is 2, and 0 plus 2 is going to give me 2 right there. So it seems like after performing this multiplication here, which we are interpreting as a transformation of a point to arrive at a new point, P prime, we have landed at the point 6, 2. So there was our resulting final location right there, P prime, 6, 2. Right? So it seems like what happened here is it seems like that point P only moved horizontally right there. Now let's go ahead and take a look at our second example and see if we can see some sort of similar type of behavior here. And this guy, again, I'm going to go ahead and call this my transformation matrix and my point vector. I know that we're going to get out another 2 by 1 new point vector that we call P prime. And so let's go ahead and perform them. Oh, sorry. Let's plot our point first. We're starting at 2, 2 again. All of these will start at 2, 2. And what I would like to do is go ahead, and by the way, I'm suspicious. I want to move that. Let's go ahead and do our matrix multiplication here. So I'm taking the dot product of 1, 0 with 2, 2. This will give me 1 times 2 is 2. 0 times 2 is 0. 2 plus 0 is 2. For our second one, we're going to do 0, 2 dotted with 2, 2. That's going to give me 0 times 2 is 0, plus 2 times 2, which is 4. That's 0 plus 4 is 4. So it seems like our new point location is now located at 2, 4. Right? That's why I moved my P indicator right there, is because I saw it was going to be in the way. So there's P and P prime right there. So you should notice in this case right here, it seems like we made a vertical adjustment to the location of the original point P. So now we should ask the questions. By how much did we adjust each of these things right here? Well, the thing that I'm seeing is that P started out being 2 units from the x-axis, from the y-axis. Its x value was 2. And after performing this transformation, notice with this 3 up there in the corner, we ended up at an x value of 6 instead. So I feel like what happened here is the x value of my point got 3 times larger by performing this transformation. Alternatively, it seems like over here, the y value of our point is the thing that got adjusted, and it seems like the y value of our point got to be 2 times larger than it originally was right there. And by the way, you should be suspicious. Was that maybe an addition by 2, 2 plus 2 to give us 4? I shouldn't have used 2 right here. 2 is sort of a teacher's worst number. 2 plus 2 is the same as 2 times 2 is the same thing as 2 squared. That makes it confusing to see what happened. But over here, I can see we didn't do addition, right? We didn't do 2 plus 3 to get a 5. We clearly did a 2 times 3 to get a 6. So it seems to me like what's happening here is this. I'm kind of also recognizing, by the way, that this matrix right here, in fact, both this transformation matrix and this transformation matrix are really, really close to being that identity matrix that we talked about in the last video, where we have zeros on the off diagonal and almost all ones on the main diagonal, with the exception of one of the terms right here. The thing that I'm noticing here is that when the term that's not 1 is in the upper left space, it seems like it was making a adjustment to our x locations. When it seems like the number that was off, that wasn't 1, was in the lower right over here, it was making an adjustment to our y locations right there. So let's kind of keep that in mind as we kind of go and look at our next examples over here. So in the third example over here, what you should notice is that we have sort of a combination of the previous two. Remember that these ones are the things that are really causing things to remain the same. Notice that when we did the dot product of 0, 1 with 2, 2, we just got back 2 again in the bottom slot. When we did the dot product of 1, 0 with 2, 2, we just got back 2 again in the top slot right there. Over here, we don't have any ones. We have a 2 and we have a 1/2. So what I want to do is kind of predict what I think is going to happen in this case. What I saw in my upper example up here was that leaving this 3 in the upper left corner was resulting in stretching my x values by 3. So here I see I have a 2 in the upper left corner, so I'm anticipating a stretch of my x value by 2, so I think this will be 4. Similarly, I'm seeing here that there's a 1/2 in the lower right, and I saw that when there was a 2 in the lower right, it seemed to double our y value. So I'm sort of anticipating that this 1/2 in the lower right is going to cause us to only keep 1/2 of our overall y value. So let's go ahead and see if we get the anticipated adjustment here associated with this transformation matrix. So it seems like here I'm going to do the dot product of 2, 0 with 2, 2 first. That's going to give me 2 times 2 is 4, plus 0 times 2 is 0. 4 plus 0 is going to give me 4. And I am also seeing that the dot product of 0, 1/2 with 2, 2. 0 times 2 is 0. 1/2 times 2 is 1. 0 plus 1 is going to be 1. So it seems like we're taking the point from the location here at P to at 2, 2 to being located at 4, 1, P prime. Now this one's a little bit harder for us to interpret because we didn't just do one type of motion. However, based on looking at the previous two examples as well, what I'm sort of picturing here is that this column right here, 2, 0, says make your x values twice as wide. This column right here with the 1/2 in the bottom slot says make your y values only half as tall. And what you can see happened with this P point here is we did stretch it out twice as wide from the origin, but we also smashed it down to only have half the height. And that's how it ended up at that P prime location right there. So this is doing the stretching horizontally by 2, compressing vertically by a factor of 1/2 right there. This does agree with as being like a combination of our previous two examples. Right? So that's pretty cool. So it seems like this sort of agreed with what we guessed was going to happen based on example 1 and example 2. But it seems like when we have these zeros on the off diagonal and some constants on the main diagonal here, these are going to represent stretching factors in the x and in the y direction associated with the points that we are transforming right here. The thing that I'm noticing is different about the next example is that it's got a negative in it here. So notice kind of, let's talk about what we think we might see here. We're again seeing zeros on the off diagonal. We're again seeing actually non-zero numbers on the main diagonal. But here I'm not seeing any numbers other than 1, give or take a negative. So what this says to me is, I don't, based on the previous 3 examples now, what we've kind of learned is that the numbers sitting in these on the main diagonal seem to indicate the amount we should stretch by. And here what I'm seeing is we're multiplying by 1 in each case. So this shouldn't change the magnitudes of the numbers. However, the fact that a negative is included does seem like it's going to have some impact on the location of this point. So let's go ahead and do the multiplication from t times p to get p prime and see where our new point is going to end up over here. So I'm seeing here we're going to start by doing the dot product of negative 1, 0 with 2, 2. That's negative 1 times 2 is negative 2 plus 0 times 2, which is 0. Negative 2 plus 0 is just negative 2. Then for our second term, we're going to get 0, 1 dotted with 2, 2. That's going to be 0 times 2, which is 0, plus 1 times 2, which is 2. 0 plus 2 is going to give me 2. So it seems like here our new point ended up over here, p prime and p. So it seems like what happened here is exactly as we thought. We didn't change the magnitudes of our numbers. They started out as 2's, they ended as 2's. The magnitudes of them stayed the same. But it seemed like this negative right here, which by the way, recognize that this negative is in the slot that was associated with a horizontal stretch in our previous examples. This was a horizontal stretch by a factor of 3. It seems like here we also made a horizontal adjustment based on the location of this term right here. But it seems like this one, instead of stretching us some amount, said negate that amount. And so what that says is if your x value is positive, it should now be negative. If your x value was negative, it should now be positive. So it seems like what this did for us right here was it performed a horizontal reflection. Seems like it took the things on the right side of the y-axis and put them on the left side. And if we were on the left side, it seems like it would have negated the negatives to make them positive, to put them back on the right side. So let's look at our last example here and make our little guess as to what we're going to experience here. Hopefully you're good at guessing these by now. Here what we can see is almost the exact same matrix as the last time. The only difference is that the negative is on the other term. You should notice that in the previous examples, having this 0 blank something right here in the second column was affecting the y coordinates rather than the x coordinates. And so here, what I'm guessing I'm going to experience is rather than a horizontal reflection, because this is not a change of my x values, this is a change of my y values, I'm instead expecting to experience a vertical reflection right here. So let's do the multiplication and see what we get. Here I'm going to do the dot product of 1, 0 with 2, 2. It's going to give me 1 times 2 is 2, plus 0 times 2 is 0. 2 plus 0 is going to give me 2. For my second one, I'm going to do 0, negative 1, dotted with 2, 2. That's going to give me 0 times 2, which is 0, and negative 1 times 2, which is negative 2. 0 plus negative 2 is negative 2. So it looks like we got exactly what we were sort of predicting was going to happen right there, which is that we started at the point 2, 2, and we ended at the point 2, negative 2. And it's so kind of the thing that I'm learning here is this. Whenever we have these zeros on the off diagonal and only actually have numbers on the main diagonal, it seems like the first column is indicating what adjustments we make to x, and the second column is indicating what adjustments we're going to go ahead and make to y. And so I think that I can go ahead and kind of, judge these negatives right here as helping us understand that we're performing reflections. And I can understand these non-1 numbers that are all positives as indicating some form of stretching our x components and stretching our y components here. All right. So what we'd like to do now that we've seen our first couple examples of a transformation matrix is let's do a few things. Let's generalize what we just saw and why it happened. Let's extend this idea so that it works with more than one point at a time. And then let's look at some other transformation matrices. Obviously, in particular, we're here today for the rotation. That's the one that we're talking about that's so trigonometry related. So, every transformation matrix we just saw in the above examples was of the form with the transformation matrix being, and I generally just state my general 2x2 matrices as A, B, C, D. So even though there's only two things in here, I'll call this A and D so that we think of them as being in the upper left and lower right slots right there. And what we saw was that the magnitude of A was representing our horizontal stretching factor. The magnitude of D was representing our vertical stretching factor, our Y component. We saw that if A was negative, then that was going to cause our X values to become negative. So that was flipping us over the Y axis when you negate your X values. And we saw that if D was negative, then the point that we were looking at was going to be reflected over the X axis. And remember, reflecting over the X axis is actually a vertical transformation right there. All right? So why does this work this way? I think that the best way to explain this is actually to think about the identity matrix that we talked about at the end of the last video. So let's consider this not very exciting transformation right here. Right? When I do 1, 0, 0, 1 as my transformation matrix, this is the identity matrix. And what we saw in the last video is that this is the special matrix that says when you perform multiplication by this matrix, nothing changes. And we can clearly see that here. The dot product of 1, 0 with 2, 2 is 1 times 2 plus 0 times 2, which is 2. And then the dot product of 0, 1 with 2 by 2 is 0 times 2, which is 0, 1 times 2, which is 2, and it gives us 2 in the lower slot right there. All right. The thing that I'm seeing right here is that this seems to be describing to me then how do we move in the plane based on the number of steps that we want to take. So what I'm doing here is I'm interpreting each column of the transformation matrix as the instruction set for the move in space. And so when we normally think about one x step in space, what we normally think is your x coordinate should get bigger by 1 and your y coordinate doesn't change. That would be one x step based on what your traditional sense of movement in the plane is. Very similarly, if I said you take one positive y step, then you shouldn't move your x coordinate at all. That's 0. But you should increase your y value by 1, right? That's exactly how we think about movement in the space, right? So the original point matrix then of 2, 2 says I would like to perform 2 x steps and 2 y steps. That's how I'm interpreting this 2, 2 right here. But what is an x step and a y step? Well, everything that you've ever graphed in your life said one x step is one step to the right and one y step is one step to the up. What we're doing with our transformation matrix is we're changing that rule set. Right? So alternatively, consider this setup right here, right? So if we did this matrix multiplication here, 3002 by 22, what we're going to get, and I hope that you can just kind of see this from before, is we know this 3 is going to scale our x coordinate by a factor of 3. So we got, of 2 by a factor of 3 to give us 6. We know this is going to scale our y coordinate 2 by a factor of 2, and so we're going to get back 4. So what I'm thinking here is this says, that 2, 2 says do 2 x steps and 2 y steps, where 3002 says 1 x step is really 30, and 1 y step is 0, 2. So this is you saying, all right, listen, what I'm traditionally used to doing is saying, if I say do 2 x steps and 2 y steps, you would go 2 to the right and 2 up. What we've done by applying this transformation matrix is saying, listen, you're still going to do 2 x steps and 2 y steps. We're just redefining what an x step is and what a y step is. Now I'm saying 1 x step is really 3 steps to the right, and did I say that right? 1 x step is really 3 steps to the right, and 1 y step is really 2 steps upwards. So if you perform 2 x steps, where each x step is 3 steps to the right, then you've really landed at going 6 steps to the right. We've got that right there. And we're saying if you want to perform 2 y steps and each y step is going 2 units upwards, then you're really going to end up going up a total of 4 units upwards. Right? We can kind of do the same thing with this guy over here. With this transformation matrix here, -1, 0, 0, 1 half, what this says again is 2, 2, again says do 2, oh man, I can't, this is so many 2's out here. I want to do 2 x steps and 2 y steps. But again, we're redefining what an x step and a y step is by multiplying by this transformation matrix. I'm thinking of this as my new x rule, and this is my new y rule, right? So this says to me that the matrix -1, 0, 0, 1 half says that 1 x step is really go backwards, go left by 1, and 1 y step is really only go up by 1 half. right? So we're really just redefining what we're saying one step in space looks like when we're multiplying by one of these transformation matrices here. The first column redefines what it means to move in the x direction, and this one redefines what it means to move in the y direction. Our base case that you're always comfortable with doing is where one x step is one step to the right and one y step is one step up. Because remember, these are x, y vertical vectors right there, x term and then y term right there. So what we're really doing when we multiply a point vector like 2, 2, oh man, I wish it would, there we go, 2, 2, by a transformation matrix like this guy right here, is we're really redefining the basis, all right, this is our fancy math word for the day, the basis of the space in which we're measuring movement. The standard basis is the one that you're always used to, 1, 0, and 0, 1. One x step is 1 to the right, and one y step is 1 up. So, the way that it's actually better to think about what we're doing today is this. Rather than actually you thinking of us moving the points when we apply a matrix transformation, what I think is actually a smarter thing for you to think of is what we're actually doing is we're actually stretching the space itself that the points are sitting on. What you should be thinking of right now is this. Suppose that we drew some dots on an uninflated balloon, and then we blew the balloon up. What you know is happening is that those dots aren't getting moved relative to the balloon, but the skin of the balloon is stretching, and so they are now maybe further apart than they used to be, or further from maybe some central point that doesn't necessarily move on the balloon. Like I'm thinking if you're like blowing up the balloon here, the very tip of it over here, it never moves relative to the mouth over here. This would be like your non-moving tip point right here. Everywhere else is going to do some stretching except for that one point right there. So maybe we would measure relative to some central point. So again, it's kind of better to picture that like underlying grid in your two-dimensional space. When we're applying these transformation matrices, it's really like we're grabbing that grid and stretching it, and the points are just getting taken along for the ride. We're stretching it, for example, 3 times wider than it used to be and 2 times taller than it used to be. And then we're saying, where would a point that started at 2, 2 end up if we stretched space? So that space was 3 times wider and 2 times taller, and you'd say, oh, well, that point at 2, 2 would end up at 6, 4 then after that. So a good thing to interpret these transformation matrices as is not moving points, but it's actually moving the space in which the points live. Again, thinking about drawing dots on the uninflated balloon and then blowing up the balloon, I think for me that's like a really good example for me to recognize when you blow up the balloon, it's not like your ink is moving, but those points are certainly going to be further apart than they used to be. You've stretched the space on which the points actually live. So that's what we're doing here is we're really redefining the basis with which we're using to make our measurements. And that's sort of what I described in words up here is our new change of basis, is our new definition of what does it mean to take one x step? What does it mean to take one y step? We're redefining that with every new transformation matrix that we multiply by. All right, so that's sort of our interpretation of what just happened right there. So we just said a second ago the 3 things we want to do are generalize what we just saw and why it happened. Why it's happening is because we're actually stretching space, not moving the points. We want to now extend this idea to work with more than one point simultaneously. Remember that yesterday when we talked about this, we said that one of the like bajillion different practical uses of matrix operations is for uses in things like graphics, right? For movies, TV, video games, all of the CGI, all the graphics that are in there, all of the locations of each of the pixels are always getting updated by performing matrix transformations. That's the computation that the graphical artists are doing underneath the hood. So what we know is that we aren't really interested in moving one pixel at a time. If we were going to do that, we could have just done this by converting to polar or something like that, doing this some simple way. What was more interesting to us is to move lots of points all at once. So that's our next idea here is let's extend this idea to work with multiple points simultaneously. You should be picturing the millions of pixels that might be in some high resolution image. And the other thing we want to do is look at some other transformation matrices. Obviously, our big one for today that we still want to hit is rotations. We'll see some others along the way here as well. Our other intention here is to upgrade our operation so that we can transform multiple points at once rather than just moving one point in space. Fortunately, because we're working with matrices, this is a really easy upgrade for us to do. So we've been building our transformations as the transformation matrix times the point vector is giving us the new point locations. All we're going to do is put some more points in our point vector right here. So I would like for us to consider the triangle formed by these 3 points, 0, 0, 2, 0, 1, 4. Let's determine the matrix that will perform some given transformation. Let's do that matrix operation and let's graph it all over here. All right. So what I'm going to do is I'm going to call these A, B, and C. So we're going to start here at 0, 0, 2, 0, and 1, 4. So I'm saying to you that we are making a triangle with A, B, and C. So I'm going to draw the triangle. And what we'd like to do is we would like to perform a reflection over the y-axis. I would also like to compress the height so that it's half as tall. So my goal is for this thing to get flipped over the y-axis and then to only actually be half as tall as it used to be. So first, let's build that transformation that's going to do that. All right, so our transformation matrix here, we know that there's going to be these zeros on the off diagonal because the stretches and the reflections always have the zeros on the off diagonal. I know that I want to reflect over the y-axis. And you should notice that even though we're saying the letter y, this is really a left-right motion that we're performing right here, right? That's really impacting the x value of our points, the positive x values, the negative x values. We want to reflect over the y-axis, so that means to me we want our x values to get negated. So I'm going to put that in the slot associated with the x terms of the basis, right? Our basis vector there, that negative 1, 0, says, hey, one x step is actually one step to the left now instead of one step to the right based on our new basis term right there, negative 1, 0. The other thing that we're interested in is compressing the height so that the triangle is only half as tall. So I know that the height factor is always going to be associated with this lower right term down here. I only want things to be half as tall as they used to be, so we'll multiply by a factor of 1/2 in that D term that's down there in the lower right. So this is the transformation matrix that's going to reflect us over the y-axis and squash us down so we're only half as tall. What we now want to do is multiply this thing not by a point vector, a single point. I want to include all the points in there. And so let's just go ahead and recognize that what we used to do was just have like a single point, like 0, 0. That would be my point A right there. Well, I'm just going to list my other points, B and C. I'm just going to list also 2, 0, and 1, 4. You should notice here that this now looks like a 2 by 2 times, now again, how many rows? 2 rows. How many columns? 3 columns. So I can see that the 2 and the 2 match, so this multiplication is legal. What are we going to get on the other end is we're going to get a 2 by 3 for this to be equal to, which is exactly what we want. We're going to get back another matrix that's exactly the same size as this one, representing the new point locations out there, right? So I'm just going to move these so that these are actually sitting above the things that we're interested in here. This is T, this is P, this is going to be P prime over here. And I'm also noticing that this is what I'm calling A, B, and C. And I'm going to write those just in blue so that these look a little bit of a different color here. This is my A, B, and C. And let's go ahead and do this matrix multiplication here and then graph all 3 of the new points that we're going to get. So we've got 6 6 dot products to do here. So the first one is easy. Negative 1, 0, dotted with 0, 0. Anytime you dot something with 0, 0, you're going to get back 0. Similarly, notice if I do second row, first column, we're again dotting with 0, 0. So I'm in the second row, first column, I'm also going to get another 0 here. So that says to me that it seems like A did not move when we did this, and that makes sense because the point at 0, 0, if you try and reflect it over the y-axis, it stays still. If you try and only keep half of its height was 0, so we still got 0. So that makes sense to me that we got that result right there. So for our next one here, let's find this upper middle one right here. So this should be in the first row, second column. So I'm going to do first row dotted with the second column. So that's going to be negative 1 times 2, which is negative 2, plus 0 times 0, which is 0, and that's going to give me negative 2. Now let's do second row, or sorry, first row, second column. Yeah, sorry. Second row, I was identifying that point again. Second row, second column now. So second row dotted with the second column, and it looks like I'm going to get 0 times 2 is 0, plus 1/2 times 0 is also 0. So it looks like I'm getting 0 right here. And you should notice that this is exactly what we should have anticipated, because this point B that was at 2, 0 is now at negative 2, 0. So it has been reflected over the y-axis right there, which is perfect. Let's go ahead and do our last column of terms right here. This should be first row, third column. So I'm going to do first row dotted with the third column over here. That's going to give me negative 1 times 1, which is negative 1, plus 0 times 4, which is 0. So in total, I just got negative 1. Then I'm going to be getting here, for the very final one here, second row, third column. I'm going to do second row dotted with the third column. 0 times 1 is 0. 1/2 times 4 is 2. And now we can go ahead and graph our 3 new points here, which are A prime is at 0, 0. So it's still sitting right there. There's A prime still at the same location. B prime is now at negative 2, 0. And C prime is now at negative 1, 2. And you should see that this did exactly what we hoped that it would do, which is that it reflected us over the y-axis, and it squashed down our height so that we're only half as tall, which I hope you find very satisfying here. So this is sort of our quick and easy way for us to go ahead and transform a whole collection of points in space. We see that we already can understand exactly how to do any stretches, compressions, and reflections just with these matrices that have 0 on the off diagonal. And we only need to pick out the terms that we want on the main diagonal to perform stretches, compressions, reflections, which is very, very cool here. So let's go ahead and look at some other nice relationships between some computations that we did in the previous video with what we're doing right now. A rectangle is formed by the points 1, 1, 3, 1, 1, 5, 3, 5. Determine that rectangle's area. Then do the matrix operation to stretch it horizontally by 3 and vertically by 2. And then let's find the area again, and then ask ourselves if we see some kind of nice special relationship here. So, by the way, you should now pause the video and do this yourself, because it's going to be just like the one that we did up above. All right? So please do that. Please do an example for yourself here, and then come back and see if yours is going to match mine. So I'm going to go ahead and, again, I'm going to call my points just to give them a name. I'm going to call them A, B, C, D. So I'm going to start with my points at 1, 1, 3, 1, 1, 5, and 3, 5. So this is my A, B, C, D. And we can clearly tell that these points are forming a rectangle. I can clearly see that this rectangle is 2 units wide and 4 units tall. So it seems like its area is going to be 8 total units out there, right? 8 square units. So let's go ahead and set up our matrix transformation now. So I should be doing my transformation matrix times my point matrix to get my new point matrix. And let me just, am I going to have, I think I can write this in here. So I think that we're going to do here our transformation matrix times the point matrix is going to give us our new point matrix here. So what transformation matrix should we be using? Well, I want to stretch us horizontally by 3. I'm remembering that the first column of our transformation matrix represents the new estimate, or our new description of what an x step is. So rather than doing 1 step to the right, I want to do 3 steps to the right as my new x step. What's our new y step? Well, rather than going up by 1 for every y step, I want to go up by 2 for that stretch of 2. So 0, 2, I think, is my good transformation matrix here. What's my point matrix going to look like? Well, it's just going to look like A, B, C, D, all written as column vectors, right? So this is going to be 1, 1, 3, 1, 1, 5, and 3, 5. So I can go ahead and look at that point matrix there. I can see this is A, B, C, and D. And what I know I'm going to get out over here is my final point matrix over here. And it should be representative of A prime, B prime, C prime, D prime. All right, so let's go ahead and do the matrix map here. And so here's the thing I'm seeing, by the way. This one's going to be, I'm going to do this in maybe a little bit smarter of a way right here. I'm going to, instead of I don't know, I feel like I was going top, bottom, top, bottom, top, bottom, top, bottom last time. Let's do the whole top row of P prime first, then the whole bottom row. So since I want to get all of row 1, I'm always just going to use row 1 for my dot product, and I want to do the dot product of row 1 with column 1, column 2, column 3, column 4 to get my 4 top slots in my final point matrix over here. You should notice that every one of these dot products is going to do 3 times the top row plus 0 times the bottom row, meaning we're never actually going to get any contribution in the dot product from these terms in the bottom row down here. So it seems like this should just be, and I'm going to do one, I'm going to say it out loud, then we're going to do the other ones fast. First row dotted with the first column is 3 times 1 to get 3, so we're tripling the top number. And 0 times 1 is 0, so we're discarding the bottom number for this dot product right here. Adding those together gives us 3 plus 0 is going to be 3. So the thing that you should notice is that really just resulted in us just doing a multiplication by 3 of the top number. That's going to keep on happening here. 3 times 3 is 9, 0 plus times 1 is 0, so we're just getting 9 for the next one. We're going to get 3 times 1 is 3, plus 0 times 5 is 0, so we're going to get 3 for C prime's x value. And finally, 3 times 3 is 9, 0 times 5 is 0, so we're going to get 9 for the x value for D prime right there. So notice that this 3, 0 just multiplied the whole top by 3. 1, 3, 1, 3 became 3, 9, 3, 9. Very, very similarly, you should see that 0, 2 when dotted with all of these columns so that we get the entire second row from the second row terms here, is always going to do 0 times the x coordinate. It's always going to do 2 times the y coordinate down here. So it seems to me like I can do this a little bit quicker and just say there's going to be 2, 2, 10, 10. And if you go ahead and double check my matrix math there, you will find that to be correct. So let's go ahead and plot our new points over here and then find the area again. So it seems like my new A coordinate location is at 3, 2. There's A. B prime is at 9, 2. C prime is at 3, 10. D prime is at 9, 10. So it seems like this is my new rectangle that we've got right here. This is my transformed rectangle. Now, one of the things that you should notice is that when we did this scaling by a factor of 3 and scaling by a factor of 2, it didn't only affect the width of the points, it shifted all the points, right? Even the point A, because it wasn't at 0, 0. Remember that triangle in the previous example was sort of, in a sense, centered at the origin, whereas this one is not. So not only did these points get 3 times and 2 times further away from each other, horizontally and vertically, but they also got that much further away from the origin. This one started 1 x unit away and 1 y unit away, and is now 3 x units away and 2 y units away from the origin. So our distance from the origin also got affected by these scaling factors out here. So this is our A prime, our B prime, our C prime, and our D prime. And now what's the new area? Well, it looks like this rectangle has a width of 6 and a height of 8. And so it seems like the overall area is 48 now. Now, how could I have been able to tell that when I applied this transformation matrix of 3002 to an object with area 8, that I was going to get an object of area 48? Well, one of the things that we saw in the last class was we saw the determinant of a matrix. And notice here that the determinant of our transformation matrix is the determinant of 3002. That's a parenthesis. And remember that the determinant of a matrix is the down diagonal minus the product of the down diagonal minus the product of the up diagonal. And you should notice that our area started at 8, and 8 times 6 gave us 48. Seems like the original area times the determinant of the transformation matrix equals the new area. So there are about a billion different ways that you can interpret a useful reason why we care about the determinant of a matrix. We're going to talk about only one of those bajillion ways in this video right here. But this is one of the very practical things to recognize, is that the determinant of a transformation matrix will tell you how much you are going to scale the area of the object described by your point matrix by when you apply that transformation matrix, right? So this is cool because this can help us find areas of objects without actually doing any of this process here. A rectangle is defined by its four vertices in the plane, and it has an area of 12 square units. We then apply a transformation of 9002, and I want to know from you, what is the new area of the triangle? Well, I can just do exactly this formula that I set up for myself right here. It seems like this should be 12 units squared times the determinant of 9002 should be equal to our new area. So this is going to give me 12 times, and notice our determinant here is the downs minus the ups, so that's going to be 18 minus 0 is 18. And if we do 12 times 18, oh crap, I don't know if I can do 12 times 18 in my head. Or rather, I can, but it's hard when I'm talking and writing at the same time, and I'm going to get 216 seems to be the new area of the new rectangle right here. Um, so this is a nice practical thing. And again, if you're thinking about this in the context of graphical design, it maybe really helps you to say, hey, listen, I currently am looking at an apple on the page that's taking up this much area. I want to scale it so that it takes up this much area. I want my x scaling factor to be a factor of 3. What should my y scaling factor be so that I end up with the apple taking up that much area? We could then solve for what y value would be necessary, what y scaling factor would be necessary to give us the appropriate determinant to get the appropriate scaling factor, stuff like that. So without even having the points available to us, just knowing the transformation matrix, I can tell how it will affect the area of the object that is contained by the vertices within the point matrix, which is really, really cool. All right, so there's a nice little application associated with some of these transformations we're doing right here in the determinant. One of the many, many applications of matrix multiplications and computations of determinants. So what other families of transformations do we have? So we've generalized this to multiple points. We've looked at why this is happening. We've seen how the determinants is actually involved in this here. Let's go ahead and look at some other transformations that we're going to see. So now that we're comfortable performing these transformations, we've seen a few general behaviors. Let's see all the families of transformations that we want to see today. There are some other ones out there. I hope that you can imagine for yourself that there's lots and lots and lots of ways that we can sort of move objects in space. Some are simple, some are complicated. We're covering sort of the easy ones here today, especially once you get into 3 dimensions. These get much, much more complicated. I don't know, not like unbelievably complicated, but some where you're going to have to learn a little bit more like general linear algebra knowledge to be able to handle the transformations that happen in some slightly more complicated settings. So it's not crazy, but it's not going to be handled within the scope of a class where we're talking about this just for 1 week kind of thing. So what we've seen so far is we've seen stretches or compressions. I'd say stretching is when you multiply by a number bigger than 1, and a compression is when you multiply by a number smaller than 1. We've also seen reflections when we multiply by numbers that are negatives. The other things that we want to look at here are shears, which I don't think is something that you typically think of in terms of your transformations. And the real one that we're here for, because this is trigonometry class, which is rotation. So let's go ahead and explore some more of these here. Let's perform the following transformations, graph the before and after, and interpret the result of what we see. So what you should see in our first 2 examples here is that just like before, we do have a 0 on one of our off-diagonal terms, but now we finally have a number sitting in one of those slots that's been a 0 all day so far today. And we're looking at one example each with the non-zero number in the upper right versus the non-zero number in the lower left right there. Our final example that we're going to look at, you should notice, is very different from all the transformations that we've done so far. This transformation matrix is the opposite of what we've seen so far. So far, we've seen always numbers on the main, like non-zero numbers on the main diagonal and zeros on the off diagonal, and we have the exact opposite of that right now. So this one, I anticipate, is going to be quite a bit different than the stretching and reflection stuff that we've been seeing so far, whereas this one seems different, but maybe related. At least we still have the 1 and the 1 on the main diagonal right there. So let's just go ahead and do them, see what we end up seeing out there. Again, I think there's going to be value in us identifying the A, B, C, D points and their new values, like the primes that we're putting on those, the apostrophe there to indicate the new one. So let's go ahead and do this here. So I'm going to start by graphing our original one, 0, 0, 2, 0, 0, 3, and 2, 3. So it looks like we're starting off with a rectangle right here. A, B, C, D. There's our starting rectangle. And let's go ahead and apply this transformation matrix here to this point matrix here. That's a D, not a P. I should make that clear. All right, so when we go ahead and do this here, let me just get a new color. We are going to get our transformed points over here. This will be our P prime. This is going to be our A prime, B prime, C prime, D prime. And let's do the matrix multiplication. Let's go ahead and do 1, 2 dotted with each of these. So let's do the whole top row, and then let's do the whole second row here. This is our scheme for doing this. So I'm going to do the dot product of 1, 2 with each of these 4 column vectors here. So 1, 2 dotted with 0, 0. Anytime you dot with 0, 0, you're going to get back 0. So I know that that's going to go right there. 1, 2 dotted with 2, 0. We're going to get 1 times 2 is 2. 2 times 0 is 0. So 2 plus 0 is going to give us 2 for B prime. 1, 2 dotted with 0, 3 is going to give me 1 times 0 plus 2 times 3. 1 times 0 is 0. 2 times 3 is 6. 0 plus 6 is going to give me 6. Finally, you should notice this is the most exciting one we've done all day. 1, 2 dotted with 2, 3. There's no zeros involved. Oh my gosh. 1 times 2 is 2. 2 times 3 is 6. 2 plus 6 is going to give me 8 for the x coordinate of the D prime point. All right. So that's a little bit weird. This is different than we've seen before. This clearly wasn't just a scalar multiple of the first row or something like that. And that's because it looks like there was some x and y component stuff that got brought into that. So let's go ahead and see what we're going to get when we do our whole bottom row down here. So I want the whole second row of the resulting matrix. So I'm going to do the dot product of the second row of the transformation matrix with all the columns over here. 0, 1 dotted with 0, 0. Anytime you dot with 0, 0, you always get 0. 0, 1 dotted with 2, 0. 0 times 2 is 0. 1 times 0 is 0. They're both 0, so we're getting 0 for that dot product. 0 times 0 is 0. 1 times 3 is 3. So we're going to get 3 for the y coordinate of C prime. And 0 times 2 and 1 times 3 is going to give us 3 for the y coordinates of the D prime point. So let's go ahead and plot these all and see what they look like now. So it seems like we're going to still be at 0, 0 for A prime. It seems like we're still going to be at 2, 0 for B prime. Oops, that's B prime. But it looks like C prime is now located at 6, 3. That's C prime. And D prime is located at 8, 3. So if I'm going to connect the rectangle the way that we would connect the dots to make this rectangle over here, I could reconnect them in the exact same way, but you should notice we're getting clearly not a rectangular shape anymore. All right, this one's going to be tough right here. I got to go. Oh, hey, that was pretty good. Good job, Tony. That was nice. And once again. All right, so this one was pretty weird right here. It seems like what we ended up doing was sort of skewing this thing, or what the name that you saw up above was shearing this thing. This is a shear where our coordinates that are non-zero in the y coordinate right here are getting sheared off to the right. Let's go ahead and see what happens when we do a shearing with the shear term being in the other slot right here. This was sort of took an upright rectangle and sheared it to the right. That was a horizontal shear, effectively. What do you think is going to happen when that 3 is sitting there? I'm sort of anticipating perhaps some sort of vertical shearing effect. So let's go ahead and do this one here as well. Let's go ahead and do it. So I'm going to plot my original. This is my transformation matrix. This is my point matrix of, A, B, C, D. So I'm going to plot the same points, 0, 0, 2, 0, 0, 3, 2, 3. There's my A, B, C, D. I'm going to connect them because I'm picturing the rectangle that they're forming. And let's go ahead and perform the shearing that's associated with this guy here. So what are we going to get out here? We're going to get out our new point matrix here, which I'll call P prime. That is going to be A prime, B prime, C prime, D prime. And what do we get? Well, first row, first column. I know that we're dotting with 0, 0 is not going anywhere. I know that dotting anything with 0, 0 doesn't change. So first row, first column is 0. Second row, first column is also 0. So I'm good with those. Those are easy. Let's do the rest of the first row. Notice that the rest of the first row, it's really like we're dotting with some chunk. This top half of this matrix looks like the identity matrix, right? The 1 and the 0. So I'm anticipating that this dot product isn't going to change anything of the top row. 1 times 2 is 2. 0 times 0 is 0. So we're just getting 2 again. 1 times 0 is 0. 0 times 3 is 0. So we're just getting 0 again. 1 times 2 is 2. 0 times 3 is 0. So 2 plus 0 is giving us 2 again. So that top half of this transformation matrix looking like the identity matrix, just the top half, did apply the identity to the top half of the point matrix. We got back the same top half. This 3, 1, though, we've seen from up above is going to have a little bit more exciting action here, so let's do it. We've already done the second row, first column. We know we're going to get 0 because the dot product of zeros with anything is 0. But for the second column here, 3 times 2 is 6. 1 times 0 is 0, so we're going to get a 6 here for the y coordinate of b prime. 3 times 0 is 0. 1 times 3 is 3 for the y coordinate of c prime. 3 times 2 is 6. 1 times 3 is 3. And 6 plus 3 is going to give us 9 for the y coordinate of d prime. So let's go ahead and take a look at what our new points look like here. So now we've got 0, 0. A prime didn't move, and things at 0 are going to often not get adjusted by transformations. B prime is now at 2, 6. Ooh, it's way up there. C prime is at 0, 3. And D prime is at 2, 9. So if I, again, connect my dots in the sense that we connected the dots with our original, A and C should be connected. A and B should be connected. All right, can I do it here? I got to go. Oh, it's hard to draw those slanted lines. That's that good. D and B are connected, and C and D are connected. So it looks like this performed a very, very similar type of shearing as the previous one, except this shearing was to skew it upwards in the y coordinate right there, which is what appears what that 3 is handling for us right there. All right. So we can see that when we have one of our off diagonal terms being 0, but the other being non-zero, it's going to introduce some sort of shearing effect where one part sort of stays still and the other part's getting either dragged up or the bottom part staying still and the other part getting slid across over to the right. It seems like the amount of component in the y is actually contributing to some stuff in the x and vice versa right there, right? So we're sort of mixing how much the x and the y. It's not just that the x components are transformed by the x component in the transformation. It's that now x and y are getting involved when we have things like 3 and 1 and sitting in that same row right there. All right, so here's two good shearing examples right here. As our final example, you should notice this one doesn't necessarily look like that shearing form. In fact, we have both zeros on the main diagonal right here, which is a little bit weird, right? So this one, I don't know what to expect as a guess as far as this one goes, but we can go ahead and, do our same math right here. Let's just do the math, see where the points go, then try and interpret what we're seeing right here from this weirder transformation matrix that looks different than all the other transformation matrices we've seen today, because the main diagonal is 0 in this case. So what are we gonna? Well, let's see what our thing looks like here. We got a 0, 0. We got a 2, 0. We've got a 0, 3. And we've got a 2, 3. All right, so our same rectangle right here. That's our A, B, C, and D. Let's do the matrix multiplication. And again, you should probably be making sure that you can do all these on your own here, and will be expected here. So let's go ahead and do it. First row dotted with the first column. Well, that's 0, so we're going to get a 0. First row, first column. First row, second column. 0 times 2 is 0. Negative 1 times 0, 0 again. First row, third column. 0 times 0 is 0. Negative 1 times 3 is negative 3. First row, fourth column. 0 times 2 is 0. Negative 1 times 3 is negative 3, so we're getting a negative 3. Okay, I can do that. Notice that this second row of our transformation matrix looks almost like what the identity matrix would look like if it were flipped. So it's not quite the same thing right there, right? So second row, first column, well, anytime you dot with all zeros, you get 0. Second row, second column is 1 times 2 is 2. 0 times 0 is 0, so we're going to get a 2. You should notice that what this just did, since it's sort of like the flipped version of the identity matrix, it took a 2, 0 point and made it 0, 2. It flipped those coordinates right there. Our second row, third column, 1 times 0 is 0. 0 times 3 is 0, so it looks like we're getting 0 for both terms for that dot product there. Finally, second row, fourth column, 1 times 2 is 2, 0 times 3 is 0, so we're just getting a 2 right there for our final term. So this is our A prime, B prime, C prime, D prime. So let's graph them and see where we end up. I think this is our one of our most exciting ones here today. So it looks like A, once again, didn't move, and that's not surprising because it's at the origin. B prime is at 0, 2. I keep on writing the numbers for some reason. I'm trying to write B prime here, dang it. There's my B prime. Looks like C prime is at negative 3, 0. And D prime is at negative 3, 2. So connecting these dots in the same way that they're connected over here, A and C are connected. There's the A and C connection now. Used to be vertical, it's now horizontal. C and D should be connected. It was the top, it's now the left side. D and B should be connected. It used to be the right side, it's now the top. A and B should be connected. It used to be the bottom, it's now the right side. So my question to you is, what operation did we really perform? What transformation did we really perform to go from this shape in black on the left to this shape in black on the right? One way that you could interpret this is that we squashed it a little and we stretched it a little and we like shifted it over or something like that, right? But if you were to interpret it that way, you should notice that your points are wrong. Because if you interpret this as like a squash and like a shift and a stretch or something like that, then it should be the case that, like, for example, C and D were on top. They should still be on top, but that's not what's on top right there anymore. Right? So it doesn't seem like this is like a squash and a shift. Instead, it seems like C and D that were on top are now the vertical component that's over here on the left. It seems to me like we took a rectangle that was upright and that we laid it down. That's the transformation that I'm seeing, is an upright rectangle. And again, look at the labelings of your four corners, and it is now oriented like this. This seems to me to be that rotation that we've been hunting for. But how are we going to interpret this as a rotation by some number of degrees? So even if you're down with this being that rotation, an example of a rotation matrix, it's certainly not clear how we would do other types of rotations based on this, but we're going to be really, really, really smart about this, and we're going to just work to figure it out. All right, so let's go generalize what we just saw right here, and then we'll come back to try and figure out how can we generalize this idea right there to do any type of rotation, not just a what, and I'm asking you right now, how much did we even rotate by right here? Think about it. All right, so what do we just see? Well, the first two performed what we would call a shear. The last one seemed to perform a rotation, right? So here's our two shears. Here seems to be our rotation that we've been looking for. Let's see if we can understand what was happening here. We can see that the transformation matrix 1, 0, 2, 1 says, for every x step that you want to do, that just says go in the 1, 0 direction. That is our one step to the right. That's the 1, 0 that we're seeing in that transformation matrix right here. However, in this case here, one y step, this says when before you used to just step up when you went in the y direction, instead, you're actually going to go 2 units to the right and 1 unit up for every thing that used to be a y step. So the thing that's weird about this one is that the things that we used to interpret as just go up, now also involve some horizontal component. What we're redefining one y step to be, instead of just go up 1 unit, is now right 2 units and up 1 unit. That's what my 2, 1 is telling me here. So the shears are weird because they're bringing in both x and y values into what you used to think of as just a y type of alteration right there. Right? These shears are really useful for changing depth perspective in graphical animation. You can imagine looking at something head on and then looking at it from the side. Things might look very long or might look very short, despite the fact they haven't actually changed sizes. And so these shears are things that we can use to change like our perspective on an object. And again, think about looking at your computer screen like head on and then look at it from like a really sharp angle. That's in a sense you're setting yourself up to view this from a sheared angle right there rather than from its direct perspective right there. So in general, we'll get that these transformation matrices that have ones on the main diagonal, zero on one of the off diagonal terms, and a actual shearing component on the other off diagonal term, these are going to perform our vertical and our horizontal shears here. All right. And by the way, I know that this is going to perform a vertical shear on this one because this 1, 0 here says my x basis term still just says go 1 to the right. It's the y stuff that's got a new term that's in it. So we're going to get extra y action there for the vertical shear and vice versa for the second transformation matrix here. The last example, the transformation matrix 0, -1, 1, 0, seem to perform a rotation, the transformation that we've really been hunting for this week. So my question to you is, how many degrees did we rotate by? And can you use that information to deduce the general form of a rotational transformation matrix? Let's go back up to our picture and see this. So our first question is, how many degrees did we rotate by in this example right here? And what I'm seeing is, it seems like we had an upright rectangle. So notice that A and C is the left side. And then we laid it down so that A and C was the bottom side right here. So if you're just looking at moving some sticks out here, it looks like and we could even say the AC vector was the vector that looked like this. And then our A prime C prime vector was the vector that looked like this. It looks like we took something upright and pointed it to the left. That's a 90-degree rotation that we're ending up seeing right there. So it seems like this matrix is maybe the thing that we've been hunting for, but this is just a really special case. I want to be able to do rotations by like 17 degrees just as reasonably, and it doesn't seem like there's going to be some super obvious way to make that happen here. So here's the thing that I'm thinking. So it seems to be a 90-degree rotation. Seems to be that the transformation matrix 0, -1, 1, 0 caused a 90-degree rotation. We want to be able to perform rotations of any number of degrees. And the thing that I'm thinking here is, I know that measuring, when we're talking about how do we measure angle components of distances, we're usually using the sine and cosine functions. So what I'm thinking to myself is, I'm guessing that our transformation matrix, our T matrix for a rotation, should include probably some sine and cosine functions. So what I'm thinking to myself is this T matrix, I'm just going to draw a big generic one right here, should look something like sine of theta or cosine of theta, and sine of theta or cosine of theta. And like, I don't know what's going to go in these. I'm just kind of like throwing out some like super generic guess right here. And what I'm thinking to myself is, it should work out to be the fact that if you plug in 90 degrees, that we end up getting the matrix 0, -1, 1, 0. So my question for you is, what should our transformation matrix look like here? Now, I'm thinking to myself, for our very first term here, it seems like say here, let's try and like just guess what our parts are going to look like right here. For this upper left term, it should be that when I plug in 90 degrees, I get out the number 0. So my first question to you is, do we get 0 from either of these when we plug in 90 degrees? When we go 90 degrees, what I can see is we have we have a 0 for our x value, but we have 1 for our y value. I want to get out 0, so I'm going to guess for myself that cosine might be an appropriate thing to use right there because cosine of 90 is 0, so that would work out for that slot. If I then look at the lower slot down here, I'm seeing that we should be getting 1 when we plug in 90 degrees. And so it seems to me like when do we get 1 from a trig function at 90 degrees? Well, at 90 degrees, our height is 1, and height is measured by the sine function. Now this negative right there is sort of bothering me, and I'm not quite sure about what to do with that. I do see that we're getting -1 here. I like to think of -1 as being associated with like, I don't know, 270 degrees for sine or something like that, or 180 degrees for cosine. It seems to me like this one's the hardest one for us to make a guess about, but I can at least make my other guess for the lower right down here. I do feel like at 90 degrees again is where cosine is going to be equal to 0. This other one up here, though, just seems to be the negative of what we had in the lower left, right? It seems to be the negative of 1. And so it would make sense to me. It would be plausible for us to do a negative sine of theta in this case right there, because then negative sine of 90 would be -1, and that would give us the appropriate thing right there. So just by kind of like guessing some things, this is my guessed version of a transformation matrix by a rotation of theta degrees. And so maybe I'll call this T sub theta for the specific amount of rotation that we want to end up doing right there. This is my current guess so far. I don't know how to guess any better than this. There's technically certainly some other options out there of some things that could have cropped up, but I can't judge that until I just like try it with an exam. I don't know how to go any further with just this amount of information. And by the way, I'm kind of I'm kind of noticing things like either of these cosines could have easily been negative cosine also, because negative cosine of 90 is just -0, which is also just 0. So it seems to me like I'm a little wishy-washy on maybe some of these negatives right here, but I think that this is at least a good guess for our transformation matrix here. So what I think we should do is take a look at this guess and let's just try it on something and see if it does the rotation that we think it's going to do. So we think that maybe the transformation matrix that looks like this, which is exactly what you said, cosine on the main diagonals, positive sign in the lower left, negative sign in the upper right, might be our general rotational transformation matrix. So let's revisit our original question and see if we get this thing to work out the way that we think that it might. Are we going to get this thing, a rotation by 30 degrees, to work out properly here? So what we want to do is let's go ahead and set up what we think we're going to get for this guy. So we want to rotate now by 30 degrees. So I want to first kind of identify what does our transformation look like here, transformation matrix. So a transformation matrix of 30 degrees should be looking like, and I just should scroll up a smidge right here. It should be looking like the cosine of 30, the negative sine of 30, the positive sine of 30, and the cosine of 30. Well, we can evaluate all these because I obviously picked a nice angle where we actually know the value. If we didn't, we just go to our calculator. That's fine. And I'm just picturing for ourselves what's the deal with our cosine of 30 degrees right here. If we're at 30 degrees, what I can see is that my x-coordinate is clearly larger than the y-coordinate right there. So I'm expecting cosine of 30 to give me the larger of the two choices. So that should be our √3/2 and a √3/2 in the upper left and lower right. On the other hand, the sine is the smaller of our two choices, so it's going to be the 1/2. So I'm going to get a 1/2 here and a -1/2 here. So I'm thinking that this is our appropriate transformation matrix to rotate a set of points by 30 degrees. So what we should do is let's state what our overall operation looks like, but immediately I'm recognizing that I really don't want to do this by hand. So we're going to use Desmos to help us out with this guy here. So let's set up our TP to be √3/2, -1/2, +1/2, positive √3/2, times the point matrix 1, 0, 4, 1, 2, 5, And what I want to know is, what are we going to get out on the other end over here? So let's go and have Desmos do the calculation for us. And even better, we're going to have Desmos graph the points for us as well. And I'll stick in my graph from Desmos right here. So let's pop over to Desmos and let's do this calculation in Desmos here. So here's our Desmos here. And remember, like we saw yesterday, like I just have two Desmoses open right now because one I'm going to actually use for graphing the points. One, I want to actually go to the matrix calculator here to have it do this matrix operation for me, right? So we need to define some new matrices. So I'm going to define T, our transformation matrix, to be equal to, I need a new matrix. And I know that what we had there was, and I'm going to kind of just pop back over real quick, was root 3 over 2 on the main diagonals, 1/2 on the off diagonals, with the upper right being negative. So I'm going to do exactly that right here. Square root of 3 over 2 should go in both of these slots. And we should have negative 1/2 right here and positive 1/2 right there. So there's the transformation matrix that we just came up with right there by a rotation of 30 degrees, or our guess of a transformation, right? We still haven't even verified this is right. We certainly have narrowed it down. We think this is a plausible guess right here. We haven't confirmed that yet. Next thing I want to do is get my point matrix in here. So I'm going to define my point matrix P, and I need a new matrix for this. Now recognize that our point matrix is not 2 by 2. I need to give it an extra column there so that we can get all of our points in there. Let's go remind ourselves what our points were. 1, 0, 4, 1, 2, 5. So I'm looking at 1, 1, 0, 4, 1, 2, 5. All right, there's our P matrix right there. And so now I can define our P, well, okay, never mind. I'm just going to write this as T times P. And there we go. There's what Desmos is informing us is going to be our P prime matrix right there. So I'm going to snip this and throw this little thing into Desmos as well right here so we can see what the Desmos work looks like. All right, so there's our Desmos computation for us. I'm just copying and pasting that into Word right now. And so again, we can see, I don't know, I'm looking at all these crappy decimals out here. I was right. I didn't want to do this by hand right there. I wanted to let a calculator help me out with some of these. So I think this is a great situation for us to do that. So here's now kind of what I want to do as my last thing. I want to have Desmos also help me graph these because it's really hard for me to graph things with these like fine measures of decimals right here. So here's how I'm going to have myself graph this thing. What I want to do is have Desmos graph 2 sets of 3 points for me. So I'm going to add an item, which is going to be a table. And I'm in fact going to add 2 tables. One table for the new points, one for the old points, one for the new points. So our original points were 1, 0, 4, 1, 2, 5. So I'm going to do 1, 0, 2, 4. Wait. 1, 0, 4, 1, 2, 5. 1, 0, 4, 1, 2, 5. So those 3 green dots are representing that triangle that we are wanting to rotate by 30 degrees. So for yourself, imagine the sticks between each of these sets of points right here. And we are imagining that we are going to rotate it by a positive 30 degrees. So I'm expecting to still see 3 dots that are in the same shape, but they're going to be all 3 rotated by 30 degrees if we did this correctly. So now let's copy some of these guys here. So our first point, 0.866, 0.5. 0.866, 0.5, that's our first point. This should be the rotated version of the green dot right here. Believable so far. Next point, 2.96, 2.866. 2.96, 2.866. 2.96, 2.866. There's our blue dot right here, which seems to me to be a 30-degree rotation of the green dot that we're looking at right there. So that's also good. It seems like that's in agreement. And finally, let's get our last point right here of negative 0.768, if I'm rounding, negative 0.768, 5.33. Negative 0.768 and 5.33. And it seems like this blue dot here is our rotated version of this green dot right here. So I'm going to change some colors right here to hopefully make this a little bit easier for some people to see here. Let's go ahead and change this to orange so that we can see them or something like that. I could even make them like, I don't know if that's helping us see them at all right there. Um, oh, I could make them thicker, right? Isn't that the... There we go. There's our 3 points in orange. And let's do the same thing right here. Let's make this bigger here in blue. So what I'm seeing here is that triangle in blue looks very, very much the same shape as the triangle that we're seeing in orange. It's just been rotated by 30 degrees in space right there. So I think that we nailed this guy right here. It seems to me like we were able to appropriately transform. Let me make a different snip than that. That one sucked. I want to shift this guy over here. Sorry, I'm just trying to make a nice graph here so that in our notes this thing looks better for us to see right here. And now I'll go ahead and grab my snip of this thing right here. There we go. So using Desmos to help us out with this, really, really, really good idea, because a lot of these computations, it's important that you understand the concept of why we set them up the way that we do and how to build the transformation matrices. But as we've seen, a lot of doing this math is just a mountain of little bits of multiplication and little bits of addition. So kind of the thing that I want to throw at you guys right now is that it seems like we got our transformation matrix correct right here. So here's the thing to think about. And again, I'm going to come back to sort of like a technology application type of thing right here. Whether you guys are sort of technology nerds or not, I'm assuming that most people are aware of the idea that there are things like fancy graphics cards that you can get for your computers. These graphical cards are referred to often as GPUs as opposed to things like CPUs, your central processing unit. The difference between a graphics card and a central processing unit is that your CPU is good at doing all of the kinds of operations that a computer might want to do mostly. It's kind of good at all of them, right? There's lots and lots of different small kinds of computations that your computer does. It does them all at different speeds. A CPU is designed to be general purpose. It can kind of do all of them pretty well. What a GPU is different than a CPU is that it specializes in doing certain types of calculations much, much faster than other types of calculations. And what your GPU is doing, since it is a graphics processing unit, is it is crazy fast at doing multiplication and addition for the purpose of being able to do matrix multiplication lightning fast. So if you have a good graphics card, what that means is that you're paying extra money to make sure that matrix multiplication happens extra fast in your computer. That's going to give you things like being able to watch things in higher quality with better resolution, with a better frame rate and stuff like that. The reason you can't play fancy video games on a crappy computer is because your crappy computer can't do the matrix multiplication fast enough to update what your screen should look like, and that's when you're seeing that you're only getting like 10 frames per second and it seems all choppy versus like a very high quality 60 frames per second or better or something like that. So when you hear this conversation about CPUs and GPUs, what GPUs, graphics processing units, are doing is they're hardware that is specially designed to make sure that your computer can do addition and multiplication much, much faster than a general purpose CPU could do, because everything associated with graphics is actually associated with doing matrix multiplication to update the location of points that are on the screen right there. So that's like kind of the technological perspective from what we're seeing right here. We're only talking about moving 3 pixels right now by a rotation of 30 degrees. It took us about 5 minutes. What we want to be able to do with our computer, with our fancy GPUs, with a really fancy, I don't know, your TV that you're watching, whatever, is we want to be able to move thousands or even millions of pixels up to 60 times per second or more, with all sorts of different things going on. Rotations, color shading changes, doing some shearings because you're changing the viewing perspective as well as doing a rotation, all sorts of crazy stuff. It is all defined by matrix multiplication under the hood. So again, when you buy a fancy computer or a fancy TV to watch things better, what you're doing is you're purchasing something that's better, faster, more efficient at doing matrix multiplication so that we can perform those visual transformations of where things are located in space, which is really cool. So my last thought that I want to go with here is just there's one other tiny thing that we should see that's a really cool, nice way to kind of like wrap up the ideas that we've seen here is this. When we rotate an object in space, my question to you is, how much should its area change by? How can we see this with our matrix transformation? So when we performed a stretching, our area obviously changed. When we performed a shearing, I don't know. Did our ooh, maybe our area doesn't change with the sharing. Ooh, that's actually interesting. But what I specifically want to ask about is rotations. You should notice that rotations isn't changing the size of the object at all. It's just moving where it's located in space. So what I think is that the area shouldn't change at all. How can we see that with its transformation matrix in general? Area shouldn't change at all. What is the determinant of the transformation matrix for a rotation? That's a T sub theta right there. I'll write that a little bit more clearly. This should be the determinant of the matrix. What do we just come up with? Cosine theta, negative sine theta, positive sine theta, cosine of theta. What's the determinant of this matrix right here? Well, it should be the product of the down diagonals minus the product of the up diagonals. So this should be cosine theta times cosine theta minus sine theta times negative sine theta. This is cosine squared. Negative times negative is positive, so this is a plus sine squared. And we get 1. So remember that the determinant tells us how much we scale our area by, and we can now see that regardless of the number of, regardless of the degree or the number of the amount of angle, rotation theta, determinant of T sub theta is always 1 by the Pythagorean identity. And so therefore the area scaling is always multiplied by 1. AKA don't change. And that makes perfect sense associated with what we think about with rotations. Rotations shouldn't change area, and we can prove that by multiplying by this matrix transformation, our area will never change, which completely agrees with what we think about there. And by the way, I do just want to point out right now, it did just occur to me as I was saying it, you should notice that shears also are not changing our area, in fact. If you are familiar with the formulas for the area of parallelograms like this, they are still just base times height. We can prove that that's going to be our formula for that guy right there. And you should notice that, for example, the determinant of this matrix is 1 minus 0, which is 1 for the scaling factor. 1 minus 0, which is 1 for the scaling factor for the area. So in fact, the areas of these two shapes are still exactly the same right there. So let's kind of summarize what we just saw right here, and let's call it a day. Let's restate what we saw. We applied a variety of transformation matrices to point matrices in the format of TP equals P prime. And you should notice this was always a 2 by 2 times a 2 by n, however many points you had. And that's always going to say the 2's match in the middle. And that's always going to result in a 2 by n matrix on the other end for P prime right there, n being the number of points. Right. All the families of transformations that we saw today are here, right? We saw horizontal stretches, vertical stretches, horizontal reflections, vertical reflections, horizontal shears, vertical shears, and rotations by theta, which was kind of like our goal for this week, is to see how can we implement rotations of entire geometric shapes in space with a matrix operation, and here it is. This is how this is being computed. For every movie that you watch with CGI, when they're rendering all that stuff, they're performing all of these matrix transformations under the hood on the stuff that you're seeing. We also saw the determinant of the transformation matrix will tell us how the area of a polygon determined by our point matrix P will scale. Does it get multiplied by 6? Does it get multiplied by a half when that transformation matrix is applied? And importantly, I'm seeing here that all of these have determinants of 1. Or I should at least say absolute value of the determinant of T equals 1. No change in area. Whereas here, these are going to have, these do change area. The determinant of this transformation matrix is not equal to 1. Right? So cool stuff here. So we saw how determinants are also associated with all these transformation matrices, and essentially what we learned this week is the very, very, very basics of how computer-generated graphics are mathematically determined right here with all these matrix operations. This is the fast stuff you're paying for if you go and spend all your money on a very fast graphics card out there, right? Is faster matrix multiplication to figure out how to draw pictures faster on your screen. So that is going to wrap it up here today for us for our final topic of the semester, which was matrix transformations. This is our last video of content for the semester. We've just got our final exam during week 16. So that wraps it up for matrix transformations and trigonometry in general here. Happy semester, everybody. I'll see you for the final exam in Canvas next week. Have a good one.